In James Cameron's sci-fi classic, Terminator 2: Judgment Day, Arnold Schwarzenegger's iconic time-traveling robot assassin, the T-800, faces off against a next-generation model played by Robert Patrick. This upgraded Terminator proves rather difficult to destroy or escape, mainly because of its liquid metal body, rendered by special effects that were groundbreaking at the time of the film's release in 1991. 30 years later, we may not have mastered time travel or created killer assassin robots capable of overthrowing humanity, although Boston Dynamics is working hard on the required technology. But a new study from researchers at Carnegie Mellon University have taken us a step closer to the T-1000's phase-shifting exploits. In a new publication in the journal Matter, the team showed off a tiny Lego-like robot that can switch between matter states using the power of magnets. Modern robotics efforts have produced both rigid and soft robots. The former have hard metal or plastic bodies, while the latter use more flexible substrates. Soft robots may have improved functionality due to their more mobile structures, but they're also often weaker and harder to control. In a press release, study lead Dr. Shengfeng Pan, an engineer at the Chinese University of Hong Kong, said, "Giving robots the ability to switch between liquid and solid states endows them with more capability." The team's inspiration to create the phase-shifting robot didn't come from Hollywood films. Instead, they give credit to a less glamorous source: the lumpy but highly dynamic sea cucumber. This leathery echinoderm lives on the seafloor and can alter the stiffness of its body to bolster its weight-bearing ability and withstand external injury. Pan and colleagues wanted to create a robot that could similarly tune its stiffness. Previous efforts to make such machines have used phase-changeable polymers embedded with magnetic microparticles. These polymers are melted by external heat sources, such as lasers, while the microparticles steer shape change when exposed to a magnetic field. These robots, however, are solid and quasi-solid machines with limited morphological adaptability, or are liquid or paste-like with low mechanical strength, poor mechanical integrity, poor controllability, and low locomotion speed. A fast-moving, robust magnetic melting machine has proved elusive thus far. Pan's team aimed to overcome these challenges by using a new phase-altering material they called Magnetoactive Solid Liquid Phase Transitional Machine. This is a composite of magnetic particles and a metal with a low melting point, such as gallium, which melts at just 29.8 degrees Celsius or 86 degrees Fahrenheit. That point could be brought even lower by using alloys, such as the gallium-indium tin mixture dubbed Gallinstan, which melts at negative 19 degrees Celsius or negative 2.2 degrees Fahrenheit. This combination allowed the robot to switch phases through inductive heating when exposed to an alternating magnetic field. The robot also had an unusually flexible liquid phase compared to more jelly-like predecessors that could flow at up to 15 centimeters per second. The robot's solid phase, on the other hand, was strong, capable of bearing the load of an object 30 times its own weight. The team rapidly put the bot through a series of tests. Its flexible form helped it climb walls, split into two halves that work together to move objects, jump moats, and as seen in the video above, escape from an enclosure that a solid robot would have been trapped in, before being remolded into its original solid shape on the other side. The researchers quickly moved past these exploratory physical tests to show off the robot's potential applications. The robots could prove useful as tools for engineering. One demonstration showed how the liquid form of the robot could become a universal screw for hard-to-access spaces by flowing into a screw socket and then solidifying. Other use cases were biomedical. In a model stomach, the team showed how the micromachine could switch to a liquid phase to wrap itself around other foreign objects in the stomach, before becoming solid again to enable both robot and its cargo to be extracted. A reverse of this test saw the robot drop off cargo at set points in the model stomach, which the authors say is a demonstration of its potential as a drug delivery system. Fortunately, the team are not planning to explore how the robots could be used to crush the remains of humanity's resistance in a distant post-apocalyptic future. Future work should further explore how these robots could be used within a biomedical context, said senior author and mechanical engineer Professor Carmel Majidi of Carnegie Mellon University. What we're showing are just one-off demonstrations, proof of concepts, but much more study will be required to delve into how this could actually be used for drug delivery or for removing foreign objects. Some people might think we're overreacting slightly in comparing these early developments to a full-on shape-shifting death robot, but in the span of little more than 2 years, research in soft robotics has gone from moving metal around on a flat surface to a small robot man escaping from a jail cell. The days of having to avoid a T-1000 or even a T-800 are far, far in the future. We hope. But hopefully, the development of soft robotics for which this technology is intended will give humanity a host of useful benefits. Another different example of a shape-shifting robot comes from the University of Tokyo. These hypnotic flying robots are able to change their structural shape mid-air, creating some unprecedented capabilities. Effectively, these bots are built in segments, and each segment has its own multi-copter propulsion unit, capable of vectoring thrust in any direction thanks to multi-axis gimbal systems. The segments are joined together, but capable of articulating in a range of different directions, and the team has worked out how to coordinate all these propulsion systems in real time, even as the structure changes shape while it flies. The concept was originally inspired by the thought of flying dragons, and the way these mythical beasts could smoothly undulate their bodies in the air. In this video, you can see the state of the team's dragon robot. It's a little wobbly and a little slow, but considering the complexity involved in controlling a multi-rotor aircraft that's continually changing its structural shape and orientation, it's highly impressive. The robot is shown beginning to handle basic tasks like pushing and pulling objects, and curling around on itself to create a flying gripper ring capable of grabbing, compensating for, manipulating, and releasing objects up to 1 kilogram or 2.2 pounds in weight. It's a pretty extraordinary idea, a flying claw of sort that could snake its way around an area, grab things, and do useful tasks with them. Another video shows the dragon using pin-like attachments to open and close large valves in upwards, downwards, and horizontal orientations. The team has been working on the dragon for a number of years now, and it's easy to see the potential of such a wildly flexible aerial platform once the flight control software gets quicker and it begins moving with more speed and fluidity. Now, the team has presented an even stranger take on the concept in the form of its new SPIDAR robot, a torturous acronym for Spherically Vectorable and Distributed Rotors Assisted Air-Ground Amphibious Quadrupled Robot. The SPIDAR is a quadrupled robot with articulating joints at the hip and knee of each leg. These joints are weakly motorized to assist with movement, but the team sought to minimize redundant motors by using the vectorized unit multi-copper propulsion units on each segment as the primary means to move the legs, as well as to lift the entire 15 kilograms or 33 pound structure into the air. As the video shows, what you end up with is an extremely slow and noisy spider robot, whose legs look weak and wobbly at this stage, but it still raises some very cool possibilities. With a little more development, this will become a 4-point flying claw gripper potentially capable of holding and manipulating multiple objects at once. Clearly, these are very early prototypes, but with a little imagination, we can see these developing into Matrix-style flying squid robots with as many arms as is practical. With propulsion units on each tentacle or leg segment, the arms aren't dead weight on the airframe. Each is support and can provide lift with varying degrees of leverage depending on where the load's at. Such machines could perform multiple tasks at once, potentially locking their free arms to embrace their structures against walls, ceilings, floors, or other solid objects where extra force or leverage is needed. It's a fascinating concept, with the potential to create some remarkable and useful flying robots with capabilities and forms we've not really seen in nature. They've been the stuff of myth and sci-fi. The future of shape-shifting robots is exciting, and there are many possibilities for what they could be used for. From space exploration to healthcare, shape-shifting robots could revolutionize many industries and change the way we live and work. Thank you for watching, and don't forget to subscribe to our channel for more interesting content.